Log on, tune in, find out. Another good idea from Cambridge.
And of course it's the birthplace of chaos and all that sort of thing. So it's a wonderful place, Andy Crew. I should have said your place was wonderful too.
Oh, thank you, right.
Debbie.
Thank you for the introduction. Thank you for the opportunity to speak here today. All right, how do I do big screen on there? It is full screen on it. Yeah, I'm at the University of California, Santa Cruz. For those of you who don't know where Santa Cruz is, we are part of Northern California, but we're sort of on the southern end of Northern California. We're close to San Francisco, not technically in the Bay Area, but sort of the next thing south from San Francisco. So it's a little over an hour away from San Francisco. We're on the Monterey Bay, so we're also close to Monterey, Carmel. And we've got a nice group of applied Bayesian statisticians there in a department joint with applied mathematicians. Leads to some interesting collaborations, although this is not one of those. What I'm going to talk about today is constrained optimization. Worked mostly with Bobby Gramsci, former student of mine, who was here at Cambridge for a little while, but is now at the University of Chicago. A lot of this work grew out of collaboration with Janitha Gray at Sandia National Labs, although Sandia Livermore, not Sandia Albuquerque. It grew out of a workshop at the American Institute of Mathematics. Crystal Lindblatter was there with us as well. So I definitely want to thank the American Institute of Mathematics, thank the National Science Foundation for some funding, as well as I did some time on sabbatical at the RAND Corporation, and I'll show an example at the end of healthcare policy. This is the thing on the bottom. There we go. So I'm going to start with a little bit of discussion of optimization expected improvement. I'm glad we've already had some introduction. And then talk a little bit more about constrained optimization and some issues we're looking with there. Our approach involving integrated expected conditional improvement, and then show some examples. So for completeness, I'm going to talk about minimization today. There are a variety of ways you can do minimization. I'm going to focus on surrogate modeling approaches, where we're going to build a Gaussian process surrogate model or emulator and use that to assist us in the optimization. Traditional approach is Gaussian process. So in the previous work I've done, we've done tree Gaussian processes. I'm actually going to go back to a Gaussian process here to make it more computationally tractable. And we've talked about these things. Basically, you fit your emulator and you find the minimum. You can search iteratively, all sorts of fun things. I've also done some work where we combine it with a fast local numerical method, and that actually makes it much faster. But I'm not going to talk about that today either. We've already talked some about the improvement function. Alex Forrester introduced it for us, and Bill Knotts gave us some explanations, so I'm not going to go into a great detail about it, but I do want to talk a little bit about an aspect of it, is that it balances the expected improvement between cases where you predict the mean to be small, in the case where I'm doing minimization, and where I'm not sure the variability is large. I might do better, but I'm just not sure because of the variability. So we get a balancing effect there between our uncertainty and our expectation. And I got a little picture here to show this. Is this top one there? So suppose this is my predicted value of my function. My emulator is predicted mean there for the emulator. It's that curve. I could, here's my best point so far. It's down there. I can think about taking a point here and say, what's my expected improvement there? Well, the mean value is up here. So it's sort of close. And if I'm doing a Gaussian process, and my predictive function will be also normal. And so I can say, well, here's my predictive distribution, and what fraction of it falls below my current minimum. And I can think of that as my expected improvement. I could think of another point here, which is in fact farther from the other data points we have. So I've got more uncertainty. So my predicted distribution is a lot wider. It's farther away from my best point so far. So on average, I don't expect to do as well. But because I have more uncertainty, I get a fair amount of mass below this point. And so the expected improvement is balancing this. Well, I think I should do well versus I'm not sure, I might do well. And so it leads to some more global exploration beyond just focusing right around the minimum, because it's taking our uncertainty into account. So that is one thing I did want to mention in terms of expected improvement. So I'm going to be thinking about constrained optimization. I'm not just wanting to find the minimum, but what I actually want to do is I want to find the minimum, and then I have a region I'm going to call C that's the valid region. And so I need to find a minimum within this valid region. It's possible I may be observing the function itself with noise, so this could be either a deterministic or a stochastic simulator. And the constraint may be a hard constraint or it may be a soft constraint. we can build both of those into the same framework. But we need to find something that is valid within a constrained region. So how do we do this, particularly in the case where we have an expensive function to evaluate, if it's a black box function. So this is common with computer simulators, where it takes a long time to run the simulator. So we have something that's essentially a black box. In some cases, we don't get any gradient information out of it, and it may take a long time to run. So how do we deal with this? I also need to distinguish between different types of constraints. What we're going to call here is a known constraint is when you know it a priori. You can write down, here's my constrained region. Typically, this is something that depends only on the inputs. So that's fairly straightforward. We're just not going to worry about things in general that where the input space is constrained. We're only going to take samples inside the valid region. What gets more complicated is when we have to run the simulator or have to evaluate f in order to determine whether or not we meet the constraint. And there I want to distinguish between two different types of constraints. One where you still get a valid value out of the simulator, and one where it doesn't return a valid value. So you try to run the simulator and it just crashes for various reasons. Maybe it numerically is unstable. Maybe you're trying to take the log of a negative number. Maybe you're trying to violate some principle of physics. These are all bad things, and they don't return values. In other cases, this may be like a policy constraint. You can run the simulator just fine, but then you get a result that says, oh, we can't use that. One of the examples that I got out of the workshop we did at AIM was where you're looking at a case where you've got a town near coastline, and they use groundwater, so they've got 4 wells in the area, but they're getting saltwater intrusion into the groundwater. And so the goal is to adjust the pressure at each of the wells to minimize the amount of saltwater intrusion into the groundwater reservoir. Well, the obvious answer is you don't pump anything out of the wells and you don't get any saltwater intrusion. However, there's a problem in that there's a town there, and the people need a certain amount of water in order to survive. So there's this policy constraint that you must pump out at least a certain amount of water for the local population. And that's a hard constraint. If you're not pumping up enough water to keep the people alive, then we're not doing the problem. So you want to minimize the amount of saltwater intrusion, given pumping out a certain amount of water, but the inputs are pressures. So you don't know exactly how much water is going to come out of the wells, or predicted to come out of the wells, until you actually run the simulator. So you have to run the simulator to find out how much water you're getting out, as well as how much saltwater intrusion you're getting. You want to minimize the saltwater intrusion conditional on pumping out enough water. So it's a complicated problem. You need to balance both things. But you do get information out when you run it. So even if you don't pump out enough water, it does tell you something about the saltwater intrusion surface. And so that's... Oh,
before you
yes.
go on, so on that hidden, there's sort of 2 categories, right? One is f does not return a valid value and you know it. The other one is f does not return a valid value and you don't know it.
Well, as long as you're not getting a value out, you can't do anything with it.
Right, then you know. But what about that other case when you...
So I'm going to talk about the middle case, so I've listed there, where you get a value out. That's what I'm going to focus on today, is when can we actually use that information in interesting ways? If you don't get a value at all, what we're calling here the hidden constraints, then you basically just want to avoid the invalid region at all costs, because it's never useful. You're wasting your time running the simulator. So you just want to avoid it. So you basically try to learn where's your valid region, where's the invalid region, and just avoid the invalid region. But in the case where you get some information out, what can we do with that? So we run it, we get some answer, we want to use it, and we can ask the question, when do we actually learn enough about the function to make it worth perhaps purposely choosing a point we think will not be valid? It may not happen very often, but it might happen from time to time. And so the idea is to come up with a criterion which quantifies how much we expect to learn about the minimum. Our overall goal is minimization. We want to learn about minimum in the constrained region, but it's possible that we may have a point that will help us that is in fact not at the minimum and not even in the valid region. So what I'm going to do is define what we call the conditional improvement. What I want to do is consider improvement at a point y conditional on observing a new point x. So normally we're thinking about just one point at a time, but now I'm going to think about 2 points. I'm going to observe a new point x. Where do I want to put x? And in picking x, how much do I learn about other possible locations y? Because eventually I want to learn about all of the space I care about around the minimum. And so suppose I add a new point y, how much more do I learn about x? Add a new point x, how much more do I learn about y? In particular, how much do I learn about whether y is going to be a new minimum? And so I want to compare my predicted value at y to the existing best known point f min. And let me come back in a bit to how I define the minimum of the function, because that gets more interesting in this situation. So I look at the predicted distribution of the response z at some reference location y, conditional on having added x. How much more do I learn? So I'm going to think about updating my emulator with the new point x, and then think about how much more I learn about y, and we can actually compare. The improvement at y minus the conditional improvement at y says how much we've learned by adding x. Question?
And you don't worry about whether y satisfies the constraints or not?
Yes. I probably should write that up here. The improvement is only within the constrained region. That should be in there.
So the improvement would be 0 for a point then.
Yes. So if y is not in the valid region, then the improvement is 0. That's a good point. It's not in our notation. It should be. Thank you. So we can say, how much did we learn about the minimum by adding this point, by looking at the change in improvements? And we can also think about this guy, because y is going to be coming out of our posterior distribution. I'm going to do all this in a Bayesian setting. So I have a predictive distribution. So this improvement is actually going to be of a distribution. So I can take the expectation, the posterior expectation of this conditional improvement. I want to talk a little bit about what does the minimum mean. First off, if we have a stochastic simulator, we don't necessarily want to take just the point that we've observed, because the point may not lie exactly along the line. It may be observed with noise or with whatever sort of numerical noise we get. So first off, I'm going to think about the predictive distribution and the mean. So I take the mean value of my emulator, and I'm going to use that rather than the individual observations. But second off, I want to look at the minimum along that predictive surface. And there's a particular reason I want to do this, and that's so that I have a monotonicity constraint for my conditional improvement. If I think about this point, so here's the bottom of my, my predictive distribution. Here's the best point I've observed so far. Let me consider this reference location y. Think about conditional improvement at y. Supposing I'm adding this new point x over here. So before I add new point x, if I just look at the improvement of y, I'm going to be thinking about this solid line here as the current predicted distribution of y. And then I can look at whatever fraction is below, say, the best point, or below the minimum of my predictive. And that's off this solid line. Now you notice that because it's below the best point, more than half of it is in fact below the current observed point. Suppose I add in this new point x. Adding in a point is going to tell me more about the predictive distribution of y, because y is close to x. So I'm going to learn something about y. So I'm going to expect to get a tighter posterior predictive distribution. It should be around my expected mean. And this is sort of the prior posterior expected. But my posterior distribution will tighten up. So you can see this dashed line here as the posterior distribution I expect to see after I've observed x. I haven't observed it yet, so I don't know exactly. But that's what I expect to see at this point. And so it's more concentrated. And so what will happen is, if I'm comparing the amount below this line here, because y is below my best point so far, the improvement actually would go up, which would cause all sorts of interesting additional complications in talking about how much change in improvement I get. If I compare it to the bottom of my posterior curve, my predictive curve, then it's guaranteed to always go down. Because any point I choose that's not here will be above it. And so since they're Gaussians, they're symmetric, it's guaranteed to be less than half, and it will go down as the posterior sharpens. And if it's right at the minimum, then it'll stay at a half. So by redefining my minimum as the minimum of the posterior predictive curve, I get a monotonicity constraint, which is helpful in all sorts of other calculations. Okay, so going on from here, what we do then is we look at the integrated expected conditional improvement. I just integrate this with respect to some density g. I can either look at it directly, and then I want to take the negative, or I can look at the difference between the expected improvement unconditionally and the conditional expected improvement. This is a constant with respect to x, so I can throw it on if I want to, and they're equivalent in that sense. How do I choose this density g? Well, if I don't have a constrained problem, I can just set it equal to 1. That gives me sort of a general global criterion. If I have known constraints, I can just set it proportional to the known constraints. For unknown constraints, I can estimate it. And so we end up just also estimating the probability that we're in the valid region. And then we can integrate with respect to that. So we're looking at improvement within the constrained region to the extent that I know where the constrained region is. So our iterative algorithm then is to just choose the next point x to maximize the integrated expected conditional improvement. And we estimate this with a Monte Carlo approximation because we can't do all those intervals necessarily. So quick example, Bobby's cooked up this function with a little bit of noise here. We draw some samples, and so suppose this is our situation so far. There's two possible areas where there might be a minimum. We've got some closer observations here, but we've got a lot more uncertainty here. And so the expected improvement says, oh, well, these are lower. Just focus on over here. That's the solid line. Says you're more likely to do better there. The integrated expected conditional improvement looks a little bit more globally. And so it's this red dashed line, and it's actually a little bit higher over here where there's a broader area to be searching. So it's thinking about sort of larger areas rather than focusing on a very narrow peak. Which is another thing our collaborators really liked at Sandia, because if you're too narrow a peak for your optimum, then try to implement it in practice. You always have a little bit of error when you try to set things up, and if you fall off the sharp peak, all sorts of bad things happen if your peak is too sharp, whereas if you've got a lot more tolerance, that's a more useful optimum in many practical cases, but we're not even necessarily trying to solve that problem. That's a side effect that they like. Suppose we have a constrained problem. So here's sort of our data so far. The area between 2 and 4 is constrained. We're not allowed to use that area. If you look at inspect improvement, then you're just going to sort of push along the end, and you're never going to sample anything inside there. If we use the integrated expected conditional improvement, then in the way we've set up this particular example, which took a little bit of work, but we set it up, you get the red dashed line. It actually says you do a little bit better sampling inside, because it's going to tell you more about the overall shape of the function. So how do we find the minimum integrated expected improvement? Just a little computational thing. We can't search the whole space, especially if it's high dimensional. So what we usually do is just throw a large Latin hypercube at it and evaluate it over that set of candidate locations. We throw in an oracle point at the minimum of the predictive mean. How do we estimate the unknown constraints? Well, we use another emulator for that. We use a classification Gaussian process and then just estimate this probability. It turns out that Bobby's found some cool ways to do particle learning for Gaussian processes, both regular Gaussian processes and classification Gaussian processes. So that allows you to do efficient updates. As you bring in a new point, it's very quick to update your model using the particle learning. And he's got it in an R package, PLGP, particle learning Gaussian processes. So a quick example in one dimension where you're constrained. Again, this is the same one between 2 and 4. You observe some data, and so we start with this Latin hypercube. Some of them are in the constrained region. Some of them are valid. And then it mostly just picks points that are valid, but once in a while it picks a point just on the edge, just inside the invalid region. And that's OK, because it helps us learn more. Here's a 2D, not so simple example where we've got this function we're trying to estimate. And suppose we have an ellipse given by the 95% contours of a bivariate normal distribution, and we need to stay inside of that. So let me show you a picture. Here's an image plot. It's got 4 peaks to it. The global minimum is actually down here outside the constrained region. The constrained region is this ellipse. And so the constrained minimum is in here, and the global minimum is out here. So we get started. Start with sort of Latin hypercube, give it something to seed with, so you can fit the emulator, and then you go updating by the maximum integrated expected conditional improvement, and we pick a bunch of points. Every so often it does go outside the regions, particularly down here. because that's where it sort of really wants to go, but it tries not to go there too much, and it does fairly well at that. At the end, we have an estimate of the probability of constraint violation, which does very well at that. But ultimately, we want to find the minimum, and it does find the minimum. So let me wrap up with a real example. When I was down at Rand, worked with a group doing, the economics group there, looking at healthcare policy issues. How do you set policies around healthcare insurance, basically, in terms of getting people to make sure everyone's insured at the lowest possible cost? So you can tinker with policies like making it mandatory. So this is in the United States, where we don't have national health care of sorts. But we do have some public programs. You can offer a public program for everybody. You can have incentives to join in. You can have penalties if you don't join into things. There are all sorts of variables you can add. You can add tax breaks for employers. All sorts of things you can do to try to influence the choices of individuals in terms of healthcare. And so what they have is a micro-simulation model. It's an agent-based simulator to help model the decisions of individuals and families as to which healthcare they sign up for, if at all. And it allows modeling different policy interventions. And so there are all sorts of statistical issues in calibration and optimization. So at the point I was involved with them, we're focusing just on calibrating the model. And what's another interesting thing about this is that it is a stochastic model, because it's based on microsimulations. But at the time I was there, they weren't ready to deal with a stochastic model. So what they would do is fix the random seed and treat it as a deterministic model. So I can show you results for using it both as a deterministic model and a stochastic model, because I know how to go in and unfix the seed. What we're trying to calibrate here is if you put in the current policies, you want to see, well, how close do you get to predicting what people are actually choosing right now? Because we have that data, and that's our one observation of real data that we can compare to. So they've got various tuning factors. The ones we're focusing on are utilities for adults and children, for each of employer-sponsored insurance, individual private insurance, and public programs. So there's 3 different types of insurance you might sign up for. And the utility of signing up for each of the one is different for adults and children. They also have constraints. They also want to deal with elasticity. So these are economists. They estimate elasticities, and they have some data where they think it should be in certain ranges. And so that's part of our objective function, is dealing with elasticities as well as matching counts in absolute error. And then the constraints relate to the estimated elasticities. They think elasticities should be in ranges like 0.4 to 0.6. But sometimes when you do the simulation, they come out negative instead of positive 0.4 to 0.6. And they say, OK, that clearly is wrong. This is sort of physically impossible. If people have to pay more for this, they're not going to be more likely to choose it. And there are certain cases where that happens in economics, but they don't think it should happen in healthcare. So the elasticities need to have the correct sign. If they don't have the correct sign, they want to throw out the run or the point completely. So that's a hard constraint for them. But even though we do it, it's a constraint, we still get an output from the simulator, and it tells us something about how closely we can match the counts. So we need to match the counts as well as meeting the elasticity constraints. So we go off and run it, and the colors aren't as sharp here as I would hope, but that's okay. You can mostly see it. This is adult and children for the employer-sponsored, the individual, and the public. And the top row is the predictive means. The bottom row is the probability of constraint violation. The darker colors are lower values. The lighter colors are higher values, trying to minimize. So what we want to do is we want to push this in the upper right. We want to push this in the lower left. And this one doesn't matter so much. But in terms of the constraints, you're more likely to have a constraint violation in the upper right here. You're more likely to have a constraint violation in the lower left there. So as with all good optimization problems, the constraints are at odds with the predictions, and so we need to balance the two. And at the end of the day, we find some answer in that case. And this is in the deterministic case. This is in the stochastic case, where we get similar answers. And so this is just sort of proof of concept if we can do this in both deterministic and stochastic cases. So just to wrap up, constrained optimization is a really difficult problem. It drives the numerical people quite crazy in a lot of cases when you can't write out the constraints very easily. So we have a statistical approach here to help, and it can also be combined with numerical approaches. And that's some of our future work, is to tie this back into direct approaches. But the use of statistical surrogate models can help speed up understanding what the constraint region is, thinking more globally. Instead of focusing on just a local minimum, we can sort of explore the space and find multiple areas of possible local optima. We've developed the integrated expected conditional improvement as a more general approach than just the expected improvement, and we can apply this in the case of both deterministic and stochastic simulators. Thank you.
Very much. Questions? Yes. John?
Herbie, I understand how the assessment criterion balances the explore versus exploit nature of the optimization. But does it explicitly make choices that would lead you to understand the constraint set better, or is that something that you have to factor in as an additional property?
It's in there implicitly. We want to do well with respect to this density. And if we don't understand the density well, it will cause us to pick bad points, which then in practice turn out to have bad improvement. So it does cause us to do some exploring of the constraint boundary. In that sense, it's not in there explicitly, and it may not be in there as much as maybe we should have it. There's certainly, that would be an option, is to include a more explicit way to learn about the constraints. So it's not in there explicitly.
I have a follow-up question. It's still not clear to me about whether the constraints are limited to constraints on the input domain, or whether you have a simulator that has, say, at least two outputs, and one output you want to minimize, and the other output has to satisfy constraints.
Oh no, that's what we're doing.
The latter is what you
Yeah.
Because you gave an example that the x-axis was the forbidden area. That's on the input domain, right?
That was on the input domain. We can do either.
Okay.
They all fall into the same framework.
Great.
The healthcare policy is we're looking at the elasticities. The elasticities have to have the right sign.
That's an output.
But the inputs, yeah, that's an output.
That's an output.
The inputs are the utilities.
Both. So, yes.
In the case where you do have information about the constraint, like in your saltwater example, where you know how much water you're getting, how does this method compare to, say, simply multiplying the expected improvement by the probability of meeting the constraint or being close to the constraint boundary? I think that's a more traditional way of handling these problems.
It's very similar in most cases. But the thing about that is that if you just multiply it, then it's always going to tell you to avoid the area where you're outside the constrained region. And we think that there may be cases where we can learn something by looking in that region, because it's going to help us learn more about the function to be able to minimize. And if you just simply multiply it, it'll always tell you never go outside the valid region.
Well, I suppose it takes into account your knowledge of the constraint function, because it's
Yeah.
a probability.
If you have a lot of uncertainty in the constraint function, then you can still get there that way. Yeah.
Yes.
Your predicted F-min, as you hit X, wouldn't that change F-min, or would it not?
Once you get the new point X, it will change your F-min. But before you've observed it, your best guess at X is on the curve. So there's this weird, what have you observed so far? You need to keep all those really carefully accounted for.
Well, yes.
In estimating the expected information, or you're doing some Monte Carlo approximation, so I guess you're sampling a bunch of points and then averaging them out. Do you have any tips or suggestions for how one might do that? We've done some experiments in a little bit different context, a discrete optimization context, where we tried estimating some of those things with Monte Carlo. We found it pretty sensitive to how you would sample and estimate.
We do try to use large enough samples. My collaborator, Bobby, knows more of the details of how that part works. So I recommend you email him on that one.
I suppose the question is which bits you're estimating analytically, which you're doing by simulation, which you're doing by...
Most of it ends up being by simulation, because there's a whole MCMC behind this as well.
MCMC.
Or, well, there's particle learning now behind this, but
So you're not-
particle learning is also simulation.
So you're not using InLab then?
No.
All right. Well, Thank you very much for being here.